In this animation, we're going to draw with rotating vectors and explore how the lengths, velocities, and initial angles affect the shape. If we rotate a single vector, we'll draw a circle. We could change the length of the vector, but we'd still get a circle. We could also change the initial angle, but you guessed it, circle. We're going to need a second vector. We'll rotate it twice as fast, which will give us a shape that is known as a limacon, not a circle. If we change the length of the second vector, we will change the size of the limacon. If we change the initial angle of the second vector, we will rotate the limacon. Now, remember that the second vector was rotating twice as fast as the first. Let's go 3 times as fast. This produces 2 inner loops instead of 1. If we rotate it 4 times as fast, we will create 3 inner loops. The number of inner loops will always be 1 less than the ratio of the velocity of the second vector to that of the first vector, assuming the ratio is a whole number and, have you noticed, if both vectors are rotating counterclockwise, or at least the same direction. But what if instead we rotate the second vector clockwise? The loops are now on the outside of the shape, and the number of loops will be 1 more than the ratio of the velocities. Well, that about covers what we can do with 2 vectors. Let's look at 3. This time, we'll use powers of 2 in our ratio of lengths and powers of 3 in the ratio of velocities. We'll start with all 3 vectors rotating counterclockwise. This produces a cool shape, but let's rotate the second vector clockwise. In my opinion, the shapes are more beautiful when at least one of the vectors is rotating clockwise. Let's zoom out and observe how the length of each vector affects the shape. We'll max out the length of the first vector at 2 units, and then take it down to 0 units, which means that this shape is really just that of 2 vectors. There weren't any distinguishable patterns with the first vector, but take a mental picture of the shape when we bump the length of the second vector up to 1.5 units. Compare this to when the length of the second vector is negative 1.5 units. Do you notice anything? We'll look again when the length is negative 0.5 units. Compare this to the original length of 0.5 units. Maybe you noticed that negating the length of the second vector has the same effect as rotating the shape 45 degrees. Lastly, we'll pull back the third vector to a length of 0.05 units, which sharpens the tips. Then we'll take it up to 1 unit, which creates this bubbly shape. But like the first vector, there are no apparent patterns, so let's move on to the initial angles. If we change the initial angle of the first vector, it warps the shape. Now the shape does repeat itself when the first vector is at 2 pi over 3 radians, as well as 4 pi over 3. But this is not the pattern that I'm looking for. I'm not trying to warp the shape. So, if we change the initial angle of the second vector, this will also warp the shape, except at pi radians, which has the same effect as rotating the shape 45 degrees, just like when we negated the length of the second vector. Cool, but still not what I want. Changing the initial angle of the third vector also warps the shape, but without repetition. Again, I don't want to warp the shape, I want to rotate it like we did with 2 vectors. Before, all we had to do was change the initial angle of the second vector. This rotated without warping. But this time, it's going to require some joint effort between the second and third vectors. If the initial angle of the third vector is equal to a negative third of that of the second vector, then the shape will rotate without warping. Now, I have not attempted to prove or generalize this, but hopefully it inspires you to search for more patterns. If you're still here, thank you for sticking around. We'll see you in the next one.